Hi everybody, welcome to lecture 25 of Electrical Engineering 331. In this lecture we will talk about transfer functions. We are going to work two examples, or maybe you could consider it three examples today, and all of them will deal with this circuit shown right here. And this circuit is also considered in problem 6.1 and 6.16 in your textbook. In the first example, example 25.1, what we're going to want to do is to determine the transfer function and the resonant frequency of this circuit. And then in example 2, we will find the response of this circuit to a particular input. In this first example, we will actually calculate the resonant frequency first, and then we will calculate the transfer function. And furthermore, when we calculate the resonant frequency, we will first determine an algebraic expression for it, and then we will evaluate that algebraic expression for these particular values of R, L, and C. But when we look at the transfer function, we will merely find an algebraic expression. We won't bother to substitute in these particular values at the end. So, as I said then, we're first going to find the resonant frequency. This is a concept we have not talked about before, so let's see how to do that. The resonant frequency is usually denoted by omega naught, and it's the frequency at which the input impedance Zn or input admittance Yn is purely real. And note that only circuits with reactive elements, in other words capacitors or inductors, will display resonance. Okay, so the input impedance, what we mean by that is simply the Fourier transform of Vi divided by the Fourier transform of the current going into the circuit. Now, if we use Kirchhoff's voltage law, we see that we have Vi minus I times j omega L plus 1 over j omega C in parallel with R is equal to 0. So already then, if we solve for Vi over I, we see that this term here in parentheses is Zn. So we already have an expression for Zn. And remember, what we're wanting to do here is to find the resonant frequency, which is the frequency at which Zn is purely real. Okay, so we just have to do a bit of work here. Remember that the formula for calculating the resistance, or excuse me, the impedance of two impedances in parallel is this. You have the impedance of one times the impedance of the other divided by the impedance of one plus the impedance of the other. And so that is what we mean by this notation right here. And then j omega L is added to that. Okay, and this expression here can be simplified by multiplying top and bottom by j omega C. And so in the top you would get R, and then the bottom you would just get 1 plus j omega RC. Okay, now once you get that, then what we want to do is to get a common denominator. So we multiply j omega L times 1 plus j omega RC divided by 1 plus j omega RC. And like I say, to get a common denominator. And when we do that, we get j omega L minus omega squared RLC. Remember that j times j is -1. And so that's how we're getting this minus omega squared RLC. And then we also bring down the R, which already is over this common denominator, so it doesn't get modified in any way. And now we have this expression. And notice that this expression is a complex number divided by a complex number. So that doesn't make it real easy for us to identify the real part of Zn and the imaginary part of Zn, which is what we would like to do, because remember, what we're trying to do here is to find the value of omega that will make Zn purely real. But we can't separate out the real and imaginary parts very easily when both the numerator and the denominator are complex. So what we do in a case like this is multiply the top and the bottom by the complex conjugate of the denominator, so that then we can get a purely real number in the denominator. And then we will be able to easily see the real and imaginary parts of Cn. So that's what we're going to do here. Multiply top and bottom by the complex conjugate of the denominator. And when we do that, we will get this. And this is just, it's basically just algebra here to get this expression, but at the same time, remember that wherever you encounter j squared, that will be equal to -1. Okay, now as predicted, when we multiply the bottom by the complex conjugate of the bottom, we'll get a purely real number down here. And so now when we go from this step to the next step, what we're doing is just we're looking up here. We're not making any change in the denominator, but in the numerator, we're grouping together the the real terms, which is just, there's just one, just r, because this term and this term they cancel each other. So the only remaining real term is the r, and everything else then is imaginary. So this r divided by the denominator is the real part of Zn, and this divided by the denominator is the imaginary part of Zn. And we want to find that value of omega that will make this imaginary part go to 0, and we call that omega naught. And make it go to 0, all we have to do is make the numerator go to 0. So we get then that omega naught times L plus omega naught cubed times L r squared c squared minus omega naught r squared c is equal to 0. Now when we look at this, we see that we have two terms with omega naught to the first power and one term with omega naught to the third power. So we'll take the two terms with omega naught to the first power over to the other side of the equation, and we get this. Now right away, you will notice that one solution is omega naught equals 0. But that is what we call the trivial resonance, and that's not what we're interested in. So for the rest of this problem, we'll assume that omega naught is not equal to 0. Okay, well, if omega naught is not equal to 0, then it's okay to divide by omega naught. And so we would have omega naught squared over here and no omega naught over here. And then divide each side by L r squared c squared and take the square root. And here we have the other solution for omega naught. Now, we would have a negative value as well, but we're not going to worry about that. This is what we're interested in, is this positive non-zero frequency for omega naught. And as I said, in this case, we'll use the given values of R, L, and C to see what this is equal to. And this is an opportunity for us to do something a little interesting that you might not have had an opportunity to do very often before. When you plug in R, L, and C into this equation, you will get this expression right here. And I wouldn't be surprised if when you've done problems like this in the past, you usually just sort of drop out all of the units and do the calculation, and then at the end you'll write down what you know the units should be, which in this case would be 1/2 or radians/second, either one. And there's nothing really too wrong with that, but you're missing out on an opportunity to give yourself a check. What I mean is, if you will carry along these units, they should all work out. If they don't, that's a very good indication that you've done something wrong with the problem. So when you just discard the units, you're throwing away the opportunity for the units to tell you something is off. In other words, what I'm saying is, let's say that you're doing some problem where you know the final answer is going to be in kilograms. Well, if you do the problem and then the final answer turns out to be in kelvins, then you know something was wrong. So it's good to check your units and make sure that everything's okay. And I'm going to show you how that's done right now. Now, if you're like me, you never can remember quite what the farads and henries are in terms of more familiar units. And so to work that out, what I always do is just try to think of an equation, an easy equation that will involve those units. Okay, for henries, I know that V is equal to L di dt, where V is the voltage and L is the inductance of the inductor, and of course di dt is the time derivative of the current. Well, V is measured in volts, L is measured in henries, I is in amperes, but this is di dt, so it's amperes per second. And so right away then, I get that a henry is a volt second per ampere. Likewise, if I want to find out about farads, farads are a unit of capacitance, and I know that capacitance is Q over V. So when I substitute in now the units, farads for capacitance, coulombs for charge, volts for V, and so a farad is a coulomb per volt. So now I've already found that it was just that easy to find the henry and the farad in terms of more familiar units. And again, the henry is a volt second per ampere, the farad is a coulomb per volt. Okay, so now let's look at what we're going to have up here. We have two terms in the numerator. They are both being divided by the same denominator. So we want to investigate these two terms. Okay, the first term is going to be, you can see up here, ohm squared farad, so ohm squared farad, divided by Henry ohm squared farad squared. So down here, Henry ohm squared farad squared in the bottom. And then the second term is going to be Henry divided by Henry ohm squared farad squared. So the second term is Henry over Henry ohm squared farad squared. Now let's analyze both of these and see what happens. Well, in this first term, the ohm squared in the numerator will cancel the ohm squared in the denominator, and the farad in the top will cancel one of the farads in the bottom. So we have 1 over Henry farad, and that becomes 1 over volt second per ampere times coulomb per volt. The volts cancel, and so we have 1 divided by coulomb second over ampere. Take the ampere to the top, we have ampere over coulomb second, but an ampere is a coulomb per second, so we have a coulomb per second divided by a coulomb second. The coulombs cancel, and we have 1 over second squared. Now what about the second term? Well, the Henry in the top and bottom will cancel, and we're left with 1 over ohm squared farad squared. But as we set up here, a farad is a coulomb per volt. So that's ohm squared times coulomb squared over volt squared. We can take the volt squared to the top and have volt squared over ohm squared coulomb squared. Now a volt, from the equation V equals IR, we know that a volt is the same thing as an ampere ohm. So volt squared is ampere squared ohm squared. And when we write this as ampere squared ohm squared, the ohm squared will cancel with the ohm squared in the bottom, and we're just left with ampere squared over coulomb squared. And an ampere is a coulomb per second, so that's coulomb per second squared divided by coulomb squared, or 1 over second squared. So this is really encouraging here for two reasons, as I say. First of all, what's encouraging is that the units are the same. And that must be the case because we're subtracting one of those terms from the other. And we simply can't do that if they have different units. So it's great that they have the same units, and what's even better is that the units are 1 over second squared, because that means that the overall expression has units of 1 over second squared, and then remember, we take the square root of it, so what will the final units be? It's the square root of 1 over second squared, which is 1 over seconds, which is what we know the units for omega naught should be. So this is great. This gives us a lot of confidence that we've done this problem correctly. And so now we proceed. And now we will go ahead and do what I was talking about earlier. We can take all the constants, we can erase all those constants inside now because we know that works out to be just 1 over seconds. And then we leave the numbers on the inside, and once we turn the crank on that, we get a final answer of omega naught is 10,000 inverse seconds, which, radians is not a real unit, so 10,000 radians per second is equivalent here, equivalent expression for omega naught. So that is the first part of example 25.1. Now in the second part, we wanted to find the transfer function. And let's look at the circuit again. So the transfer function is just VO of omega over VI of omega. And VO will be this parallel combination times I, and VI is equal to that parallel combination plus j omega L times I. This is just a voltage divider here, you notice. So let's see how this will go. So again, H of omega is VO of omega divided by VI of omega. VO of omega is I of omega times that parallel combination. VI of omega is the current times Zn. We already noted that before, where Zn is just j omega L plus that parallel combination. So the i's cancel, and so we have 1 over j omega c in combination with r divided by Zn. So that's 1 over j omega c in parallel with r divided by j omega L plus 1 over j omega c in parallel with r. Now this 1 over j omega c in parallel with r, we've already analyzed that once, so I'll do it a little more quickly this time. So we have 1 over j omega c times r divided by 1 over j omega c plus r, and that's, we get that there and right here. And then we bring over this j omega L. And in both of these two terms, the one up here and the one down here, we can multiply the top and the bottom by j omega c. So we have r divided by 1 plus j omega rc there and there. And we just bring down the j omega L. And then we multiply this numerator by 1 plus j omega rc and the denominator by 1 plus j omega rc. And so we're just left with r in the top. And in the bottom, we hold j omega L times 1 plus j omega rc plus r. And so if we, in the denominator, we multiply this out and then separate the real part and the imaginary part, we'll have this. The numerator is purely real. So this is one way we could write the transfer function for this problem. Now, I'm going to star this because I'm going to find this a convenient form to return to later. but I'm going to do a little more work here, and this is not. Let's see. Okay, so this is not something you would always need to do, but of course, to check the multiple choice answers, you will need to make your answer look like the multiple choice answers. So anyway, one thing that you might consider doing is to divide top and bottom by r here. So that's sort of done and going from here to here. And then what I want is to put this into magnitude and phase form, and that's pretty easy. If you'll just remember that if you have a fraction that is a complex number divided by another complex number, then the magnitude of that is equal to the magnitude of the numerator divided by the magnitude of the denominator. And the phase is equal to the phase of the numerator minus the phase of the denominator. Well, here's the magnitude of the numerator divided by the magnitude of the denominator. And the phase of the numerator, since this is a positive real number, the phase is 0. And the phase of the denominator is just the inverse tangent of the imaginary part divided by the real part. So that's how we get this. And so our final expression for h of omega, if we want magnitude and phase form, is this. And by the way, in problem 16, there's a mention of the standard form for the transfer function. That is not this. That's still another form, and we're not going to worry about that in this course, so don't worry about that. Now, before we move on to our next example, I want to make a couple of observations. If you look at this, h of 0 is equal to 1, and h of infinity is equal to 0. Does that make sense? Well, let's go back up here to the picture and see. If omega is equal to 0, that's the DC case, and at DC, the inductor looks like a short circuit, and so this entire voltage VI falls across here, and so VO is indeed equal to VI. So it certainly makes sense that when omega is equal to 0, the transfer function is 1. On the other hand, as omega goes to infinity, the impedance of the inductor becomes extremely large, and so all of VI will drop across the inductor, and there will be no voltage drop here, and so indeed then VO will be equal to 0, which is consistent with the transfer function being equal to 0. So sure enough, it does make sense that VO of 0 is 1, the HO of 0 is 1, H of 0 is 1, the transfer function, H of 0 is 1, and H of infinity is 0. That does make sense looking at the circuit. So the last thing we want to do in example 25.2 is we're still looking at this same circuit, but we say if VO of t is what we want to find VO of t if VI of t is the sine of 1 over square root of LC t. In other words, we're looking at a sinusoid with a frequency equal to 1 over the square root of LC. Okay, well, we know that in problems like this, it's real easy to get the answer. All we have to do is to find the magnitude of the frequency response at that frequency and the phase of the frequency response at that frequency, and then modify the input accordingly to get the output. Now, from that equation star above, we had h of omega written in this form. And so when you evaluate that h with omega is equal to 1 over square root of LC, this becomes really simple. Because if we evaluate omega in the bottom at 1 over the square root of LC, notice what happens. In the bottom here, this becomes R minus 1 over LC times RLC. So the LC's cancel, and we just have R minus R, which is 0. So this part goes away, and we just learn that with R divided by J times the square root of LC. And so therefore, H at that frequency is simply R times the square root of C over L, when we invert that to take it upstairs. R times the square root of C over L times e to the minus j pi over 2. And therefore, VO of t will be R times the square root of C over L times the sine of 1 over the square root of LCT minus pi over 2. But the sine of something minus pi over 2 is minus the cosine of that something. So the final answer is VO of t is equal to minus R times the square root of C over L times the cosine of 1 over the square root of LCT. And a good exercise would be to try to get this same answer using phasor analysis. It is quite similar, but there are a few little differences, and I think that it would be worth looking at to give you a little more practice with the phasor analysis. But of course, you're going to get more practice with this technique in the test. So in fact, I think that these examples in this lecture will enable you to do test 25. And so that's it, and good luck.